and we also have some stations in the Socorro region. Last year, the highest magnitude earthquake was a 4.49, which happened near Carlsbad, but other interesting earthquakes that happened last year were 2 magnitude 3 and higher earthquakes near Albuquerque. So these were earthquakes which was very close to the Rio Rancho neighborhood and was also detected by USGS and felt by several people. Okay. The reason I work in Southeast New Mexico, because this is an area of active oil and gas operations which has seen extractions in the 1960s. However, from early 2000s, due to enhanced oil recovery, the rate of oil production has significantly increased, and with that, wastewater injection or saltwater disposal, which many people call it, has also increased. Both of this increased has correlated with the significant rise in earthquakes in New Mexico since 2020s. Before that, we were getting around 50 earthquakes every year. Now we get around 450 or higher. And we have a network of 10 stations, the red triangles, in that area, which was originally set up to monitor the WIP, which hosts radioactive waste. But now, with this significant increase in seismicity, we are looking for plans to expand our network and also upgrade our instrumentation, because that really helps with earthquake detection and location. Okay. So the main objective of this project for me was to understand seismic background noise on individual stations. And that's important because each station has different kinds of local site conditions, instrumentation type, and surrounding cultural noise. And getting an understanding of the background noise is really helpful, because if a station has high background noise, that impacts the data quality and subsequently earthquake location. In this map, I'm showing the stations, but I'm also plotting the roads and the topography and the thousands of injection and wastewater disposal wells. What I'm trying to show is that most of our stations are located very close to cities like Carlsbad, Hobbs, or Hall, and has a lot of industrial or cultural noise in those areas. And these are impacting our data quality. So the methods that we used is, we took 5 years of continuous seismic data for the 10 stations and then calculated the power spectrum density at different periods. For me, I'm interested in the short periods where we get a lot of the cultural noise and also where we get the data from the local earthquakes. In these 2 figures, what I'm showing are 2 stations. One of them is this one, which is located near a Guadalupe mountain, far away from any kind of cultural noise. And the station is well within the high and low noise ranges and has very good data quality. Over here, this is a station located very close to Carlsbad. And then at periods where I'm interested in, has a lot of anthropogenic noise, the station is very noisy and almost crossing the high noise threshold. When we look at the station maps for different period ranges, here what I'm trying to see is how the different stations have different kinds of noise. One of the things that interest is these 3 stations. They are far away from the city and industrial operations and have the lowest noise. When we check the data in terms of if a station is noisier during the day due to cultural noise or noisier during the night, we see that most of our stations is very noisy during the days as compared to the night. When we look into more temporal variations, like if summer months are noisier, and this may be effect of site conditions, if a site is very windy, or if the site is on some kind of geological structure that impacts the sensor, we don't see very good correlations. But one interesting thing that came up is these 3 stations, which are the noisiest during winter, are all located at much higher elevations than the other stations, like around 200 meters difference. And that might be an effect of the local site. Another thing that we checked is looking at the data, comparing it weekdays and Sundays. And the reason for that is looking at how industrial operations was impacting us. And as expected, we found that all of our stations right in the middle of all of the oil and gas production sites are the noisiest during the weekdays, whereas these ones far away in the mountains or away in like ranching lands have no impact of weekdays or Sundays. When we just look at raw data over here, I'm showing one-day plots of a station located very close to the VIP site. And this is a Saturday, and this is a Monday. And then this is the mountain time, so we can see on Mondays at around 6 a.m. till 5 p.m., this is like a lot of noise in the data. And not all of this is signal we are interested in. Not all of this is earthquake data. It's just trucks driving around, heavy machinery, and then we might have signal within this data that's very difficult for anyone to locate or pick from. When we look at another period range where we get a lot of our local earthquake data, we see similar results as the days being much noisier than the nights, and then most of the stations are very noisy in this period ranges, and similar to weekdays being the noisiest. The next thing we tried to check is how these individual stations was impacting our earthquake detection capabilities. For that, what we took, I took 1 year of data, earthquakes that happened in this region, and then for each earthquake, I tried to figure out how many stations helped to locate that earthquake. When we do that, we see that some of these stations, they helped in earthquake location, or we could manually see the P&S and pick the data with very less error. These two stations almost detected all of them, whereas these stations only helped in locating around 50 or 20 earthquakes. Now, when we see the stations, we can see that these stations are far away from where the earthquake is happening, whereas the other stations, they are located right in the earthquakes cluster. But even though stations being farther away, stations being on good or quiet lands is helping a lot more in earthquake location than being very close to the station or the earthquake. The next thing I tried to check, and I'm still working on, is seeing how local site conditions or surface geology might be playing a role in the station seismic noise conditions. So here I'm plotting a map from the Bureau Lithology, and then I'm only showing the surface rocks in those regions. These two stations, they are located on unconsolidated sands, mostly aeolian deposits, as we can see from the data. So even though these soils are easy for us to dig in and put the sensors in, the detection rates from these two stations is much lower. However, if we go to these two stations, which are in some kind of sandstone or anhydrite materials, mostly rocky lands, the detectability is much higher. So sometimes these local site conditions play a crucial role in the background noise. So the next steps for this project, this is a project in progress for me, is to assess the noise levels before 2010s and after 2010s, which is when the enhanced oil recovery started, and see how much at each station, at the same station, the noise level changed after introducing all of these wastewater injection wells or different kinds of drilling material. The second thing is we have stations from other networks also in this region. So if I can get those stations' data and get the maps, that will help us to narrow down on how local site, each site, is impacting the noise. And further studies on subsurface geology can help us more on understanding how much the local site is dependent. One other thing that I think is interesting, but I don't know how much results I can get from, is understanding the effects of wind patterns. So these are some initial data that I just got from NOAA's, and this was a study that was done by the National Weather Service in Albuquerque. And all of these shows that during the summer months, it's very windy in southeast New Mexico with wind speeds around 10 miles per hour. And our stations, even though the seismometer is buried inside the ground, we have a lot of surface equipment with towers of around 10 meters, steel towers, batteries, and solar panels. And so understanding the correlation of wind patterns with our temporal variations might give us some more insights. All right. Thank you, that's all.
We do have time for questions. There's time for one question. If anybody has
Okay. Yeah, thanks for a really nice talk. For your assessing the level of background noise since oil and gas production, do you have a hypothesis on like what sort of noise you're going to see? Like, do you expect to see more noise from, say, a drilling rig? And is that a frequency that's going to be easy to identify in a seismogram?
So all of the anthropogene, like drilling rigs, trucks, or people jumping around will be in those 0.2 seconds or that period range. So if we just look at those period ranges, like pre-enhanced oil recovery or after that, that might be helpful to understand. And if I can somehow get hold of like when more injection wells were drilled in, those dates might help me more to understand the changes.
Any other questions? Is there any way to look at these noise patterns and recognize a different pattern that would be different from the seismic activity during an earthquake? So can you see whether the noise patterns have a certain, I don't know, like a mark, or that you can identify them?
If I take a known earthquake and just look at this data and divide it into the period ranges, and let's say 0.2 seconds, and if I'm guessing if I look during the day and the night, I can expect to see the effects of cultural noise on one earthquake and not much of the cultural noise on that earthquake happening in the middle of the night.
I'm wondering if you can identify a certain pattern so you can filter it out.
Yeah.
Yeah, wonderful. Thank you so much. So our next talk is by